we are ready for compositions of functions, which is different than combinations. Combinations, again, is the addition, subtraction, multiplication, and divisions of functions. Compositions is different. It is a function of a function. And this is the picture that we can draw that illustrates that. Here is our regular function box. Ready? Here's our function box. What I'm going to put into my function is the domain, which is x. And so what happens is it gets operated on, some function operates on it, and what pops out of this is f of x. Okay, now a function of a function is when you take the output of one and you put it into the input of another. So this is traveling down our conveyor belt and it's getting put into another function called g. So what went into g was not x this time, but was f of x. So what comes out is not g of x, but g of what we put into it, f of x. And so this is a function of a function. This is called a composition of a function. If you've seen this before many times in textbooks, they will indicate it with a little circle. Fog or goth is what people call that. But this means f of g of x, g of f of x. It is a function of a function. We could reverse the order and draw a picture of f of g of x similar to this, but that's what we can think about. So in this first one, which is number 22, they ask us to find f of g of x, g of f of x, and also the domain of these. So we'll talk a little bit about domain. First, let's just do this. Let's find f of g of x. If they ever ask me to find fog, this has a very little meaning to me. So I immediately rewrite it into this, f of g of x, which has a lot more meaning to me. I think of evaluating this kind of like order of operations, please excuse my dear Aunt Sally, where if you had more than one parentheses, you start with the innermost parentheses. Here, I'm going to start with the innermost parentheses. I'm going to replace g of x right here. In fact, I'll try to be careful with color. I'm going to replace g of x with what it's defined to be. So g of x right here is defined to be 2x minus 7. So I'm going to go in here to the f function and write 4 times something squared minus something plus 10. But the something that I put in for x is not going to be x, it's going to be 2x minus 7. So I'm going to go in here and put 2x minus 7. 2x minus 7. That's what I'm going to put in here. All right, now when I evaluate this, you use order of operations. So when I see a parentheses, these are not like terms, so there's nothing to do in the parentheses. So I move on to the exponents. I must square that. So this is going to be 4 times 2x minus 7 times 2x minus 7 minus 2x minus 7 plus 10. So it goes like this. This is going to be 4 times 2 is 8x minus, oh, sorry. I'm going to leave the 4 out here. I'm going to go ahead and square these first. I could distribute the 4 to this, but I think it's easier to go ahead and multiply these two together first. So that's why I'm doing that. 2x times 2x is 4x squared. Negative 7 times 2 is negative 14x. Negative 7 times 2 is negative 14x. So a negative 14 plus a negative 14 is a minus 28x. Negative 7 times negative 7 is a positive 49. I'll distribute this negative right here. That's going to be minus 2x plus 7 plus 10. Now I'm going to distribute my 4. I find it easier to do this way. 4 times 4 is 16x squared. 28 times 4, I do not know. That's 232. 8 and 112 is 112 minus 112x plus 49 times 4. Oh wait, that's 3. That's 16, 19. 196. 196 minus 2x plus 17. Okay, collect like terms. 16x squared. 112 minus 2 is minus 110, oh no, minus 114. X, 196 plus 17 is a 3, that's 13. 11 plus 213. That's what f of g of x is. Okay, the other way, g of f of x is not as complicated, so yay, not as complicated. G of x, f of x goes like this. G of f of x would be g of, what is f of x defined to be? It's defined to be this right here. So let's put that guy in there. 4x squared minus x. 4x squared minus x plus 10 is going to go in there. So that means when I come to the g function, I replace the x with whatever's in there. So this is going to equal to 2 times something minus 7. What I put in there for the x is whatever I find in here, which is this. 4x squared minus x plus 10. I'm going to distribute 8x squared minus 2x plus 20 minus 7. I'm going to collect like terms. 8x squared minus 2x plus 13. The last thing to do is to consider the domain. So the domain, here's the deal. You can only allow into the f function, whatever can go into the f when I'm looking at this. So whatever's in the domain of f can go in, plus as long as whatever comes out of f is allowed into the domain of g, then I'm okay. If something that's coming out of f of x, the y values, is not okay to put in g, I have to restrict that. This is a pretty easy case. What f can accept into his system is all real numbers. What g can accept into his system is all real numbers. So whichever way I combine these, if I take f of g of x, he can accept everybody, and g of f of x, he can accept everybody. So there's no restrictions I have to make. So the domain of either one of these functions, f of g of x or g of f of x, is still all real numbers. That's its domain. Let's look at the second one real quick. 24 is two other functions. They give us, the first one that they give us is 6 over x. F of x is 6 over x. So now we have a rational function, all right? So there's a domain issue right there we could have. And then the other one is g of x is 1 over 2x plus 1. Okay, there's a couple of domain issues. So let's look at this. 24, f of x is 6 over x. And g of x is 1 over 2x minus 1. Okay. So let's look at the gray box up there that talks about what a composition is. It explains what a composition is, kind of like I did right there. And then at the bottom it says, where x is in the domain of g and g of x is in the domain of f, when they've explained it this way, okay? And so we have to be careful about what's going into the other one is still okay to accept. So when we look at these, first, let's find f of g of x, see what happens. All right, f of g of x goes like this. This is f of g of x. So I'm going to put in 1 over 2x minus 1. And then this is equal to 6 over, instead of x, I put this, 1 over 2x minus 1. Okay? And so this is equal to, I can simplify this. I can flip it. Okay? 6 over 1 times 2x minus 1 over 1. And so together this is going to be 12x minus 12. That is what f of g of x is equal to. Okay, now let's talk about the domain. First, we have to say what is in the domain of g of x, okay? We can't let any x in that's not okay to be in the domain of g of x. So what is the domain of this? You can't divide by 0, so right here, 2x minus 1 cannot equal to 0. So 2x equals 1. X is not allowed to equal to 1/2. This is a restriction we have going into this thing. Okay. Then secondly, whatever comes out of this function, whatever values we get out of this function, cannot equal to 0 because f is 6 divided by x. And so we can't let anything coming out of here equal to 0. But this is interesting. when you look at this, when you have a fraction, any fraction, a over b, the only way a fraction will ever equal 0 is if the numerator is 0. The top part is 0. Look at the top part of this. It is a 1. 1 doesn't magically turn into 0, so we don't have to worry about that. The only domain issue we have here is it can't be 1/2. So the domain is negative infinity to 1/2, 1/2 to infinity. That is for f of g of x. Now let's do it the other way. G of f of x. What about g of f of x? What happens here? Well, that's g of 6 over x. 6 over x. Okay, 6 over x. Okay, what's the g function? This is it. It's going to be 1 over 2 times whatever. I replaced x with whatever's in there. 6 over x minus 1. That's what it ends up being. Okay, we can simplify that, and we will, but let's just stop for a second. What's in the domain of f? Well, x can't be 0. That's a restriction. X is not allowed to be 0. Okay. Now, the second thing is, we can't let whatever comes out of g of x cause this to be 0. Okay, so let's go ahead and clean this up. This is going to be 1 over 2 times 6 is a 12 over x minus 1. Okay, and so this as well cannot equal to 0. So is there an x value that would cause this to be 0? We could solve for this. We get 12 over x is 1. Multiply, we could cross multiply and get 12 times 1 is equal to x times 1. Also, x cannot equal to 12, because if x is 12, we have 1 minus 1, and that's another division by 0. So, I can, so also x cannot be 12. And we can write this domain, I'll do it real quick. Negative infinity to 0, 0 to 12, 12 to infinity. All right. Now, I don't want you to get real nervous or worried about the domain for compositions, because I understand it can be kind of hard to figure out. But I do want to make sure that I've shown this to you and that you've seen it. So I don't want you to get real anxious about it. Is she going to do a lot of test questions on this? No, I'm not. I might give you the domain of compositions of function with the division, which was in the last video. Be ready for that. But this one, don't so worry about it so much, but I wanted to make sure I showed it to you. I do, however, want you to be able to simplify some monster like this. This is a complex fraction. Let's make it look better. How can you simplify a complex fraction? There's two ways you can do it. You can first find a common denominator here and add that together, and then it would be a nice keep, change, flip. Or you can do what I'm about to do here and simply multiply the numerator and the denominator by the lowest common denominator. So if I do that, which is x, what's going to happen up here is I get 1 times x over x times 12 over x is 12 minus x. This is a simplified version, and that's what that composition of functions is. Now, I think I'm going to take a pause and do the applications in a separate video because that was a lot to talk about.